and we will speak about convexity and polyconvexity. Patrizio.
Thank you very much, Samuel, for the invitation. Thank you very much, Francesco, for this nice event. I'm truly happy to be in front of you and to speak here. I will talk about Hencky-type energies. The relation to generalized continuum mechanics will become clear at the end of the talk. Hencky-type energies are well known. They are used in elastoplasticity for describing finite strain, and they are based on the logarithm of a tensor, of the stretch tensor. And I will talk more or less about issues which come with such formulations, and my central result today is that there is a possibility of making these energies elliptic and even polyconvex. I shall acknowledge a joint work with Dumitrel Giba, Johannes Lankert and Robert Martin from my group in Essen. So here, the Hencky strain tensor, you take the matrix logarithm of the right stretch tensor. It's a positive definite matrix U, and you take the logarithm, which means basically that you diagonalize U, and then you apply the logarithm on the diagonal. Mind you, the logarithm itself can be applied also to non-positive definite symmetric matrices, but then things get a lot more complicated. But in this talk we can restrict attention to this case. We have a lot of nice properties of the matrix logarithm, namely look for example at the incompressibility constraint. It's just a trace of the log, because the trace of the log is a log of the det, and this being 1 means this must just be 0, and so incompressibility is easy. You have a natural additive volumetric isochoric split. The logarithm can be splitted in this part, isochoric part, volumetric part, and it separates additively. In elastoplasticity you use it because you have a code running for small strain plasticity, and if you use the logarithm you just uplift all algorithmic relations and you have a code running for finite elasticity. There are many other properties. You have basically everything that is needed. Just look at this nice property. The logarithm, the matrix logarithm, generates a monotone matrix function. If you take the scalar product on matrices, you have this monotonicity. It's not so difficult to show, but I didn't knew it some time before. Here a little bit of history. Usually the logarithm is going with the name of Hencky. In the 1930s he introduced the Hencky strain energy. I will come to that in a moment. But in fact the history is much older. Usually people using Trustel's books go back to Ludwig in 1909, where there is just one sentence. We use the specific elongation, which is the logarithm of a one-dimensional quantity. No explanation, nothing else. This is a non-reference, but it's written down in Trustel. But now the history is unfolding. I found recently an article by George Ferdinand Becker, an American scientist, who is introducing the logarithm into a nonlinear elasticity relation from an axiomatic point of view. And I have put down on a table a complete work where we try to understand what Becker does, and in fact I can tell you he does the same thing as Hencky. The only thing is he is not using the Kirchhoff stresses but the Biot stresses in the end, in 1893. And even before, Imbert, a French researcher, used a one-dimensional logarithm for describing rubber elasticity in Marseille. So the history is old, and the logarithm has some intrinsic advantages. So here's the Hencky energy. You take the deviatoric part of the logarithm, which is the isochoric part, the trace part, which is the volumetric part. You can write it in terms of the eigenvalues, and here I have my notation. F is a deformation gradient, U is a right stretch tensor. The eigenvalues mu and lambda are the Lamé constants of infinitesimal elasticity, shear modulus, bulk modulus, and so on. So this energy is used and has been introduced by Heinrich Hencky in 1929. By the way, I have undertaken the labor of translating the original works of Hencky from the German to the English, so that you might just look at our webpage and to read it, because I find that intriguing that Hencky is not just introducing this energy, but he has a plan and he has an axiomatic deductive approach to it. And it is very well written in German, and I hope we have transmitted this into the English translation, so if you are interested. So this is a little bit of history of Heinrich Hencky. He was a little bit unfortunate, a rheological pioneer, and he did his PhD at Darmstadt, my alma mater, and then tried to find a permanent position. He even went to the MIT, but they didn't like him. He was too theoretical at the time. Then he had some years in Russia, but of course, because of political problems, he couldn't stay there. He returned to Germany and survived the war somehow. And just died at 65 in a climbing accident. So these are the original papers. Welche Umstände bedingen die Verfestigung bei der bildsamen Verformung von festen Körpern? And I invite you to look at his original development. I'm not going now to talk too much about Hencky, just one property, which is his axiomatization. He wants to have an energy which is independent of any reference configuration. That is, regardless of where you are in the process of deformation, if you add an increment of load, the load increment should be uniquely characterized by the corresponding deformation increment. And if you do this, and here I have a picture, you have the load increment, the final load increment is the same one, but you have another initial configuration, but still you want to have that the corresponding stresses are the same. If you want to have this, so the stresses are just determined by the increment of the load and not where you start from, then there is only one choice to do that. It's the Hencky energy. And the stresses which go with it. So this is the result. There is a unique characterization of this energy. There are many nice properties. You have automatically the correct behavior as the determinant goes to zero, or the tension compression symmetry. You have a good experimental evidence for it. If you have, let's say, up to 30 to 40% strain, for an isotropic material, Anand has shown that the Hencky energy is practically the best one. It satisfies the Baker-Erickson inequality. It satisfies the Hills inequality, which just says the energy should be a convex function in the logarithm of u. And we have this decoupling. So more advantageous properties, it satisfies the Valanis-Landau separation hypothesis. It's an additive function in the eigenvalues, the fits. You only need two Lamé constants for describing a nonlinear response. And the other things have been said. And more, but the energy is not Legendre-Hadamard elliptic. That has been shown by myself in my PhD thesis, and then in many other works, for example by Bruns and by Bertram and co-workers, which have a more general picture on that. So this is well known, which says, of course, that if you don't have ellipticity, you can stop thinking about mathematical well-posedness. It doesn't mean that the model is not useful or not even nice, but just for mathematics it stops the picture. Also, it is not coercive, so if you control the energy, but the energy has only subquadratic growth for large deformations, you somehow have not enough control for the energy, for the deformation. So this is a problem. Here you see a one-dimensional picture. It looks nicely convex. It's just a logarithm, one-dimensional squared. But in the red region, you have a non-convexity, and this starts from E, the number E. And if you have a bigger picture, you see this is the behavior of the Hencky energy, and you see this lack of growth. It's just getting flatter and flatter, and you have no way to work with it. This is just for the uniaxial case. So no general existence result can be expected. and you lose, for example, that the Cauchy stress is an invertible function of the logarithm when you pass e, the number e. Here you see the Cauchy stress, the one-dimensional, you have a peak, so up to here you could say it's somehow nice, it's increasing, and then it drops down. So in the red region it's a bad model. Of course you can say that the red region is of no interest because you are looking at small strains anyway, and this is even not 40%. This is 270%. But the mathematics needs ellipticity or control everywhere. So our challenge and our conjecture is the Hencky energy is still the best geometrically nonlinear deformation description, but it has the problems. So what are really the points which single out the Hencky strain energy? Because of lack of time, I have just to tell you that I have recently been able to motivate the Hencky energy by a reasoning which is completely devoid of any mechanical argument, but from differential geometry. It's a long story, I could talk for a day about that. The story goes as follows. You work on the group of invertible matrices. On that group you introduce a Riemannian distance. The choice for this distance is not arbitrary because the final result should be objective and isotropic. This fixes your metric. You look at geodesics on the group with respect to this metric. You want to find the distance of a deformation gradient f to the group of rotations in that group. You parameterize your geodesics. You see that you are not able to solve the geodesic equations, but you want to know the distance only to the group of rotations, and by some luck you are able to compute the distance without being able to compute the geodesics. And the result, the geodesic distance of the deformation gradient to SO3 in the group of invertible matrices is nothing else but this energy, Henky's energy. No choice, no assumption, practically no assumption. And this convinced me that this energy has something to it which singles it out from all other energies. You can write down whatever you want with invariance and so on, but you don't have this differential algebraic, differential geometric, argument. But regardless of what you do, this guy is not elliptic. So last year,
all other energies are all other quadratic energies.
Good point. And this is already the issue now. This energy is not elliptic, but what I show is that these individual parts, the deviator of the logarithm and the norm squared and the trace of the logarithm squared are the good ingredients for an energy, and we could now look at a nonlinear expression being expressed not just in the logarithm but in these items individually. Is it possible to find an energy which uses these input variables and in the end is elliptic, rank 1, convex, and so on? The answer is yes. Yes, it's possible, and since I talked about this last year in Montreal, there the discussion just put me into this direction, what one can do, and I want to thank Professor Segev for somehow asking the right questions about the nonlinear response, and that made me think about it. So here's a picture. Just to make my statement about this geodesics. The sphere is somehow a picture for the group of GL, of invertible matrices. It's not the correct picture because GL is not compact. You have a subgroup, the group of rotations. Your deformation gradient F is living on this group. You ask yourself, where do I have to go to SON on the shortest way? This is a geodesic. You have to find the geodesics. By that way, you have also to find the optimal rotation, which is it? And the answer is twofold. The optimal rotation is always the polar orthogonal factor of f of the polar decomposition. You decompose f into its orthogonal part and its stretched part. So the nearest rotation is the polar rotation, and then the distance, the length of that curve in a complicated expression is just the logarithm of u. And I'm able to weight this distance, and the two weighting parameters are just mu and kappa, the bulk modulus and the shear modulus, which you can see in the metric. So this is our main result, and we can even specify this. If I only take the isochoric part, then I get the deviator. If I only take the volumetric part, then I get the logarithm. Okay, so good. I could show you more motivations for that. Recently, Cristione has introduced the same invariance augmented with a third one, and he calls the first one amount of dilation, magnitude of distortion, and he has some other nice properties which come with these terms. They are somehow orthogonally decoupling the response for the Cauchy stresses. So the point now is, the strain measure, the logarithm of u as a strain measure, is nothing special. I must make this point very clear, because you can invert any strain measure in terms of any other strain measure. I could use the Cauchy-Green strain measure and so on. So on the level of strain measures, there is no difference between the logarithm and any other strain measure. But what I'm saying is not that I'm using the logarithm, which is a no statement. I am using a specific expression in terms of a logarithmic argument, which are these two arguments. Not every isotropic energy can be written as a function of these two arguments, because I'm taking the absolute value. And not every isotropic function can be written in terms of these two arguments, while Cristione shows that in terms of these three arguments it can be expressed. So now, because of time constraints, I have to skip a little bit. Here is our energy, the one-dimensional picture. I told you for a very large range of strains, from 0.7 to 1.4, the response of the Hencky energy, which is the blue line, is a very good one. The nonlinear response is basically of that type, and if you look at practically all materials, the basic feature is you lose elastic modulus in tension and you increase in less elastic modulus in compression. So this is very well fitted. The question is, however, how should you continue in the big deformation regime your response? The Hencky energy itself is somehow going down, and we would like to have something which goes up, because this is somehow the convexity which you want to have. And so we looked for a replacement of our energy. The first one which we found is the Basant approximation. The logarithm is approximated by that guy. You see it here in the one-dimensional picture. The logarithm is somehow degenerate. You replace it in the vicinity of the identity by that expression. It's already convex in the one-dimensional picture, but it's not a nice replacement for all deformations. So here was another guess. Just take the exponential of the Hencky energy. You take the Hencky energy and you exponentiate it. Look at the one-dimensional picture. This is the replacement. It's convex. This is the basic observation which I had very early. If you have a logarithm squared, here is a logarithm squared, which is a non-convex function, and you take the exponent of that guy. There's nothing cancelling. Exponent of logarithm squared is a convex function of x. So our guess was, take now the Hencky energy as a whole, put it in the exponent. Here you see my expression for that. If you now look at the stresses, then you have a nice monotone relation. However, the function is still not Legendre-Hadamard elliptic, rank 1 elliptic, and here I just recall what rank 1 ellipticity means. It means if you perturb your deformation gradient by a rank 1 family and you have convexity with respect to T. And now it's known, and that's what I said before, that energies which are quadratic in certain strain tensors are not rank 1 elliptic. This result in its generality is Bertram, Silhavi and Bölke. So our energy e to the log u for simplicity, just the simple part of the Hencky strain energy, is not convex in U and it's not convex in F. Of course, we don't want to have neither convexity in U nor convexity in F. The question is whether it's rank 1 convex. Here again the picture, the logarithm is not convex, e to the logarithm squared is convex. However, this guy is not convex, not polyconvex, we knew that long before. Is by chance, is this guy polyconvex, ranked 1 convex, or is this guy polyconvex, ranked 1 convex? Let's see. We have used a criterion of Damisch-Dykman, which expresses the energy, the isotropic energy, in terms of the invariance, the principal invariance, and formulates a polyconvexity statement in terms of the energy as functions of the invariance. Here you can see this. You want to have convexity in the invariance and a certain non-decreasing property in the first two invariants. And we checked these properties by numerical sampling just to get an idea, and it turned out that it looked good. It looked good. The statement that we could finally prove is in 2 dimensions. This energy, now we are not taking the exponential of the Hencky energy, but we split our contribution, the isochoric part of the Hencky energy and the volumetric part of the Hencky energy, and we exponentiate both individually and add them up. This guy is rank 1 convex in 2 dimensions. And in fact, we seem to have a proof that it's also polyconvex and it satisfies every growth condition that you have. That means in 2 dimensions you have a complete existence theory. And if you look at moderate strains and you compare the new energy, the exponentiated Hencky-type energy, with the Hencky-type energy itself, the difference is nothing, practically nothing. So for 2 dimensions we are settled. But in general, e to the log in 2 or 3 dimensions is not ranked 1 convex. In 3 dimensions, it's not ranked 1 convex, and the volumetric part is always ranked 1 convex because we had just this 1-dimensional property of convexity. However, in 3 dimensions, the new energy seems to be rank 1 convex on a very large domain, which includes the bounded distortions. If you control the distortions, not just the deformations, if you control the distortions and you have a bound on the distortions, a pointwise bound, the number is 27, so arbitrarily large, then it seems to be rank 1 convex. So for applications, everything is fine. In 3 dimensions. In 3 dimensions. In 2 dimensions, everything is okay. And we seem to have shown that in 2 dimensions it's polyconvex. Now I have some other properties of constitutive inequalities which I don't have time to look at, but let me now switch in the last 5 minutes to an application in Kossora elasticity. So in Kossora elasticity, micropolar elasticity, I'm writing down for convenience a quadratic energy in the first Kossora deformation tensor, which is this U bar. It's the rotation, the independent rotation transposed times the deformation gradient. A quadratic energy, U bar minus 1 is the strain measure. You have the symmetric part, the skew symmetric part, the trace part, and here I factor out the traces. And you have a curvature expression which is isomorphic to the to the second Kossora deformation tensor. So a complete nonlinear model. The question is, what can you do? The parameters are shear modulus, Kossora couple modulus, bulk modulus, and a length scale. This is more or less known. We investigated the properties of that model, the mathematical properties. We have an existence proof for several variants in that isotropic model for the minimization problem. Either you control the skew-symmetric part, then everything is more or less trivial. You couldn't gain any mathematical medal for it. So I was interested in the problem where you don't control the skew-symmetric part locally, but you have just the energy. This part, a symmetric expression, the volumetric expression, and the curl. The curl again is isomorphic to the second Kossora deformation tensor because you let the curl act on rotations. It's a very tricky business, but it works. So look now at the question of strain measures for a Kossora continua. If the energy is 0, then look at the energy being 0. What does it mean? If the factors are positive, then each item in itself individually must be 0, and that means only u bar equal to 1, the identity tensor remains. U bar equal to 1 means that the deformation gradient f is a rotation. R transpose F is a rotation. F being a rotation but also a gradient means it is a rigid rotation. So you have a rigid configuration. 0 energy means rigid configuration. Very nice. And simple. Now look at another version. I keep the curvature, I keep the symmetric part, but I replace the volumetric expression by a true volumetric expression. Here you see the first time the log of u bar, the log of a non-symmetric object, but this is cheated because the log of the trace of the log is the log of the det, and the det of R transpose F is just the det of F. That means this is just a volumetric expression controlling the volumetric part of F. Again, if you have the energy is 0, it turns out that you control this, the first deformation tensor to be 1, even without controlling the skew-symmetric part, because the interaction of the term is like that. You write that down, and you don't need the skew-symmetric part to have that property. I find that interesting. We have modeling and existence for this first nonlinear, materially nonlinear version long ago. Now let's switch to our logarithm. Again, we go back to our quadratic expression, but in terms, but instead of u bar minus identity, we insert the logarithm of u. The logarithm of u bar. Now things get tricky. The logarithm of really a non-symmetric matrix, which means you have to solve the matrix exponential, and you have to consider all solutions of the matrix exponential. Again, we have the skew-symmetric control here. If the energy is 0 and you have each individual contribution, then u bar must be identity, a rigid rotation. If you skip the skew-symmetric control locally, then you have still a rigid control. The only thing is now you have a rotation, the Kossora rotation, and the deformation gradient, and both are rotations and both are rigid, but they do not coincide. Yeah, this is an extra statement. No one is saying that a rigid configuration consists of these two rotations coinciding. No, a rigid configuration for a generalized continuum consists of the rotations, the independent rotations being rigid, one rotation, and the deformation gradient being rigid. Whether they coincide depends on additional assumptions. And what you see here, the individual terms, they have an interpretation in terms of the introduced measures which I motivated before in the Hencky-type energy. The infimum over all rotations of that guy, the deviatoric symmetric part of the logarithm of R transpose F, etc., is just the geodesic distance which we saw before. The trace log is independent of the rotations anyway. It is this guy, and if you take the infimum with respect to rotations over the skew part, then the best rotation you can choose is the orthogonal factor, which makes this positive definite. You take the skew part, it's 0. So here we have now, again, the statement, 0 energy implies rigid situations in basically all situations, with the difference, if you control the skew-symmetric part, you fix the rigid rotations to coincide. This is what the skew-symmetric term does. And now, look at our Hencky energy. I'm writing basically the same object in terms of now the energy for the Kossora model. I take the deviatoric symmetric part, I take the exponent, I take the trace log part, and I take the exponent, and I have my curvature part. Again, you control, the rigidity control is there. This is what you have. And you could now introduce a kind of gauge condition, that is, you have a freedom in rotations. You have to fix them, for example, by boundary conditions. And this also gives you a clue how to couple rotations to deformations, because the mathematical formulation somehow tells you need to do that, and you need to do it in the right way. And now my final statement is this one. The first term is the same, no surprise now for us, but now I am changing also the curvature expression. The first curvature expression is practically the second Kossora deformation tensor. The next curvature expression is the curl of U bar. Now you could think what strange curvature measure is that, but it turns out that this guy here is still only depending on derivatives of the rotation by the specific combinations which you have. It's not depending on the second derivatives of f, which are in U bar. I mean, U bar is R transpose f. You take derivatives, you expect derivatives of f to appear, but they cancel out. And the final curvature expression which I like is the curl of the log of U bar. This cannot be more crazy, so the log is everywhere, in the local part and in the curvature part. For all choices you have, if the energy is 0, you have a rigid iteration. And why I'm inclined to take the curl of the log of U bar, because I have a mathematical statement which tells you the following. If the log of U bar evaluated at the boundary in tangential direction is 0, then you have the following estimate. The symmetric part of log U bar plus the curl of log U bar estimates the full log U bar and the curl log U bar. And that will be the first step towards a mathematical existence proof for such a most general Kossora model based on logarithmic strains. Thank you.
I allow for one single question so that Patrizio can prepare the next presentation next year. So you have to find a good idea for him. Okay, Victor.
Patrizio, there are different definitions of logarithm of non-symmetric equations. In your contribution, you are writing logarithm of n-symmetric tensor. What do you mean?
Yes, it's any solution. It's any solution of the exponential equation. So it's a multi-valued object. I had to treat with this object in several algebraic problems, which had to be solved first when considering the polyconvexity and convexity stuff. And there is many more to say about the logarithm. It's a complicated issue, but basically all solutions of the exponential equation. A multi-valued object. By the way, I have put it here on the table, several printouts of all the slides and some other papers. Thank you.
Thank you again. And then